Hello, and welcome to NICER 201, online course on causal inference from observational studies, COSIT. We are talking about the topic of p-values, and this is the third session where I'll talk to you and discuss with you some of the misinterpretations of p-value that are found in literature. P-value is the probability that the test hypothesis is true. This is not correct. For example, if a test of the null hypothesis gave p as equal to 0.01, the null hypothesis has only a 1% chance of being true. And if instead it gave a p-value of 0.04, the null hypothesis has a 40% chance of being true. This is what this would mean, but that is not correct. In fact, p equal to 0.01 would indicate that the data are not very close to what the statistical model, including the test hypothesis, predicted they should be, while p is equal to 0.40 would indicate that the data are much closer to the model prediction, allowing for chance variation. Second, p-value for the null hypothesis is the probability that chance alone produced the observed association. Again, this is not correct. For example, if the p-value for the null hypothesis is 0.08, then it doesn't mean that there is an 8% probability that the chance alone produced that association. In fact, p-value is a probability which is computed assuming that chance was operating alone. Third misinterpretation, a significant test where we say significant based on p less than or equal to 0.05 means that the test hypothesis is false or should be rejected. Again, remember that small p-values may be true, but it may also be because the data is unusual, and it can be held to be true only if all the assumptions that we use to compute this p-value were correct. It is possible that we do not meet those assumptions in our study, especially in observational studies. This could result from large random errors, this could result from violation of study protocols, and even violation of the test hypothesis. Similarly, looking at the other side, non-significant test results or large p-values does not actually mean that the test hypothesis is true and should be accepted. Large p-value is evidence in favor of the test hypothesis. Not necessary, because any p-value which is less than 1 would mean that the test hypothesis is not actually the hypothesis which is most compatible with the data. Any other hypothesis with a larger p-value than what we got would be even more compatible with the data. Hence, what we need to do is actually examine the range of confidence intervals, which will give us a better idea of our compatibility of the data with our hypothesis. Based on the p-value, a large p-value, we cannot make a definitive conclusion that there is no association between the exposure and the outcome of interest. Another misinterpretation is that null hypothesis p-value more than 0.05 means that no effect was observed. It shows an absence of any. Here, the most important parameter is not the p-value, but the point estimate or the observed association. Unless this point estimate or the observed, the odds ratio or the risk ratio, rate ratio, risk difference, whatever we are calculating, difference in proportions, etc., unless that equals the null value exactly, it is actually a mistake to conclude from p more than 0.05 that the study found no association or no evidence of an effect. The best measure of association or the best measure of effect is the point estimate. Again, it is wrong to think that lack of statistical significance indicates that the effect size is small. Why? Because large effects may not be detected as statistically significant if your sample size is small. So again, confidence intervals, which we will talk about in subsequent sessions, can help us to determine whether the effect size are of any importance or not for the purpose of our study. Is p-value the chance of our data occurring if the test hypothesis is true? Not really. P equal to, for example, 0.05 does not mean that the observed association that we are seeing would occur only 5% of the time. It refers not, remember, p-value is not just what we observe, but also more extreme observations. Another misinterpretation of p-value is that if you reject the test hypothesis because the p is less than or equal to 0.05, the chance that you are in error, the chance of making or being false positive is 5%. Again, this is a misinterpretation. Suppose the test hypothesis is true, and if your test hypothesis is null hypothesis, that is true, then if you reject the null hypothesis, either you may be right or you may be wrong, which means the chance that you are in error is actually 100% and not 5%. 5% here refers only to how often you would reject it over many uses of this test across different. So if you did the same study multiple times, in how many studies is there a possibility that you would get a result as extreme as 5%? So 5% is so if you did 100 studies, in 5 studies, you will get a result which is of this value or more extreme. It does not refer to the single use of this test in one particular study, because in one particular study, we don't know whether the p-value and that you're getting, could it be because it's true, or it could be because of any assumption violations or random errors or protocol deviations. Does p equal to 0.05 and p less than equal to 0.5 mean the same thing? Again, no. P equal to 0.05, it just says that it's just borderline in terms of statistical significance, whereas p less than equal to 0.05 says that your data is compatible. So it's with borderline as well as incompatible with the model. Again, both of these interpretations are not really something clear, and we may want to avoid making such kind of interpretations. What we see in literature many of the times is that p-values are reported as inequality. P less than 0.02, p more than 0.05, etc. It's always better to actually report the actual exact p-value. So if the p-value was 0.015, please report it as 0.015 and not as less than 0.02. If the p-value was 0.06, or p-value is 0.7, again, see that those are very different p-values, but when you put it as p more than 0.05, it does not convey much information. So this is generally a bad practice to report p-values as inequalities less than or more than, because it makes it very difficult for the reader to actually interpret the results. Of course, if your p-values are really very small, something like less than 0.001, then it's okay to actually, instead of it's 0.000000 something, it's okay to then report it as less than 0.001 or 0.0001 or likewise. Statistical significance is a property of the phenomenon being studied, and thus statistical tests detect significance. Again, this misinterpretation is promoted when researchers state that they have or they have not found an evidence of a statistically significant effect. When actually speaking, the effect that is being tested, either it exists or it does not exist. It's not about how statistically significant that effect is. The statistical significance is just a dichotomous description of the p-value, where we have chosen a cutoff. Mostly it is 0.05, and we say level below this is statistically significant and above this is not statistically significant. And so this is just a property of the result of the statistical test. It's a property of the p-value, not of the phenomenon or the effect that you are trying to study. Should one always use two-sided p-values? Not necessarily. Whether to use a one-sided p-value or a two-sided p-value would actually depend on what your test hypothesis is, what is the practical significance of whether it should be one-sided or two-sided. For example, if you're comparing two drugs, and there's a new drug and there's an existing drug or a standard drug, and you're trying to look at, say, survival time, what we would want is that the new drug should be at least as good or better than the standard drug. So here, the question is one-sided, and hence here, testing this hypothesis, we would use a one-sided p-value. When the same hypothesis is tested in different studies, and none or a few of the tests are statistically significant, which means across different studies, which means here statistical significance meaning all p-values in all of these studies or most of these studies is more than 0.05. So we can say that the overall evidence supports the hypothesis. we cannot reject the null hypothesis. This belief is often used to say that literature says that there is no effect of this exposure on the outcome. So, but we should remember that suppose, let's say there were 5 studies, each had a p-value of say 0.10, which means none of these is significant at this 0.05 level. However, when you combine these p-values and we use what is called as a Fisher formula, and if we were to calculate a pooled overall p-value by combining all these 5 studies, we would actually find that the p-value is much lower. And in fact, it may actually be as low as 0.01. Right? So there's the lack of this so-called statistical significance in individual studies cannot imply that overall there is no evidence of any effect of the exposure and on the outcome. Again, similarly, it says that when the same hypothesis is tested in 2 different populations and the resulting p-values are on opposite side of 0.05, maybe one is less than 0.05, one is more than 0.05, we usually report that the results are conflicting. We're not sure whether there's an effect or no effect. Again, remember that before we make that conclusion, we need to look into how these 2 studies were done, what were the study populations, what was the hypothesis being tested, and so forth. So maybe these 2 studies are not comparable at all. And even if they were comparable, it is not necessary that all assumptions were being met in both of these studies. Similarly, when the same hypothesis is tested in 2 different populations and you get the same p-values, it is not a good practice to report that the results are in agreement. Again, because of the same reasons, because this may be, even though we're getting similar result in the 2 studies, but again, remember that these are 2 different populations, and the way the study was done, whether the assumptions are met or not, have to be looked into before we make this kind of an inference. So here we have seen various ways in which the interpretation of p-values is done incorrectly or p-values are misinterpreted in literature. We hope that you will be more considerate when you interpret the p-values from your study and do not fall into the trap of making these similar mistakes. Thank you.